we are going to start this webinar to talk about the presentation of the FIB Bulletin 97, and we will have this index that I will do a short opening, and then we'll have an introduction of the bulletin by Guillermo Ramirez. Then we will talk about the different aspects. I will tell you a little bit just after some minutes. And then after all the presentations, we will have a turn of Q&A, and we will ask you to ask your questions in the Q&A part of the webinar. So I will start now. Before that, it's the opening that will be done by myself and David Fernandez Ordóñez, the FIB Secretary General, and I will tell you a little bit about the FIB. Okay, the FIB is the merge of two former associations from the 50s, the CEB and the FIP. And in '98, both associations that were collaborating for many years, they created what today is the FIB. And well, we have already 41 statutory countries that as FIB is a federation, we have 41 countries. And but we have members from more than 100 countries. So we have really an association that is dedicated to structural concrete that is very widely represented in the world. The FIB is organized around the general the FIB, and it's because it's led by the countries. And then we have a technical council that is taking all the main decisions, and we have a board that is the presidium. And the secretariat is behind the presidium. And then we have all the commission, task group, and working parties. They relate to the technical council. That is the main technical body of the FIB. As you can see, we have many commissions. Today, we are presenting a document regarding Commission 5 reinforcements. This is a task group within this commission. I don't have time to explain all the task group in the FIB, but I can tell you we have more than 70 task groups developing documents and working to develop documents for structural concrete technology. We have several ways of publications. One is the journal, Structural Concrete Journal, that is now in a good position in civil engineering with a good impact factor. Yes, so something interesting here is for researchers to publish papers that are for free. And now with many countries, you can publish open access papers also for free, because there are some agreements with some countries, for example, like Germany, Spain, Italy, many other countries. So I would recommend you to take a look, and maybe you can publish open access for free. And as we are today with a lot of people from practice, we have a kind of paper that is very short. We short project notes, and it's more simple than a research paper. It's 3 pages, and it's dedicated to nice projects. So maybe I would recommend you, maybe with the nice work that you have done or done with your company, to try to bring some of these works to the journal. And then we have the bulletins. We are presenting today one of the bulletins. Because as you can see, we are from many different kinds, from prefabrication to fiber reinforced concrete or submerged tunnels. As you can see here, we are talking today about pre-stressing. So there's a lot of information about this. You can find all of them in the FIB website. And I would like to tell you that we have in our website, FIB subscribing members and associate members, they can look at all the FIB bulletins, CEB documents, FIB documents. They can see in a viewer that is embedded in the website. So this is something very interesting if you want to find the document and take a look at that document. Okay, and please follow us in our social media and in the website. There is all the information available is in this page. Okay, and now I will introduce briefly the speakers. The first one is going to be Guillermo Ramirez, that is a member of the group External Tendons and a secretary of the Commission 5 reinforcement since 2010. And he also is a civil engineer in the Polytechnic University of Catalonia and works for VSL, as you know, a pre-stressing company. Then we'll have a presentation by Dr. Hermann Bayer, who is a member and secretary of the task group External Tendon, and he's also a structural engineer from Germany and manager, director of matrix engineering, mainly active in design of bridge strengthening and research and development of structural products like post-tensioning system and ground anchors. Very active. He's also the co-chair of the commission. And then we have Teddy Theriot, who is a major bridge design engineer in Florida, Department of Transportation, and also the FID Commission convener of Task Group 5.8 and a member of another working party. So it's also a person very dedicated in post-tension and any bridges. And finally, we have Christian Glasser, who is also a doctor in civil engineering from Munich and a consultant in post-tensioning. And he has a career in Diviator. Now he's CTO of Diviator, and he is member of some of the task groups of Commission 5, 5.3, 5.6, 5.8. And of course, he's very active in many other places. So he will talk about testing and inspection. Then after the presentations, we'll have a closing and a question and answers. So I would ask you to post all your question and answers in the Q&A link that you have there. And then at the end, every one of the speakers will answer those questions and we have a discussion. So now I would ask Guillermo to share his screen. I will stop sharing mine.
Thank you, David. Thank you, everybody, for joining today, and good afternoon. As you've heard, we'll be 4 speakers today. I encourage you all to post your questions on the Q&A section. There's a dedicated button somewhere down there. And then we will run through the presentations one after the other, and we'll address all the questions at the end. Therefore, it will be very helpful if when typing the question, you could write who are you asking to, and then that would simplify our process at the end and make smooth and direct answers. So, well, thanks again, and let's start. What are external tendons? External tendons for bridges, as we will refer to them throughout this webinar, are tendons that are unbonded tendons, which are made of pre-stressing steel, which means high-strength steel and low relaxation. These are tendons that are external to the concrete section, as opposed to internal tension, as shown there, and external to the concrete section, but located within the limits of the structural depth, as opposed to, for instance, extradosed cables. The FIB Bulletin 97 that we are presenting you today is covering the use of these external tendons on bridges, because bridges are the sort of structures for which the technology was first developed and mostly used. But there are, however, no limitations for application for the same technology for other uses. A typical example today is the use of external tendons in wind towers. But let me go back to bridges to explain a bit the story of that. So the history, the concept of post-tensioning has been recognized for over a century now. And interestingly, early development started with external tendons. If we go back to 1888, the engineer Peter Hugh Jackson filed a patent on internal and external post-tensioning concrete pavement. 30 years later, Eugène Freycinet and Jean-Charles Seaille filed a patent, this one on internal bonded post-tensioning, with the novelty that it was using high-strength steel. It is the use of high-strength steel which soon enabled the crystallization of all these ideas and patents into actual structures. In 1934, Franz Dischinger filed a patent, this one specific on our subject today, external post-tensioning of bridges. And shortly after that, the idea was brought to reality. And the first post-tension concrete bridge with external tendons was built in Aue, Germany. The tension was applied by externally arranged bar tendons using steel that could be restressed to compensate for the losses in stress due to creep and relaxation. Due to lack of maintenance, the original bridge had to be replaced, but not before having provided good service for almost 60 years. In the picture, you can see a view of this new Aue bridge that was rebuilt according to the original design. 1938 saw a couple more of early applications of external tendons using steel bars together with some innovative techniques. In or near Stockholm, the Klockenstrand Bridge, designed by Häggblom, was built also using external tendons made up of steel bars. And in Wiedenbrück, Germany, a bridge was built using external tendons that were stressed by application of the so-called system Finsterwalder, after his inventor. This system is based on stressing of the tendons by direct action of the self-weight of the structure. Fast forward, during World War II, many military structures had been built using internal tendon, which helped to develop and popularize this technique that soon became the state-of-the-art for concrete bridges around the globe. The steady progression of pre-stressed concrete in the 1950s, 1970s, stimulated by the reconstruction of Europe, requested efficient construction technologies for bridges, which contributed even further to the development of the post-tensioning with internal, and therefore very few applications use external tendons until the late 1970s, when there was a resurgence of external post-tensioning in major bridge construction. The design of larger bridges pushed the application of bigger tendon units, and these big tendons could not be embedded in the concrete webs without significantly increasing the web dimensions, which would have driven to big increases in the structure self-weight. The need to minimize this self-weight was a driver for external tendons. Additionally, precast segmental bridge construction started to be more common. The use of external tendons in this kind of structures allowed to fulfill the need for continuous tendons through the joints. One of the first major applications of external tendons took place in the 70s for construction of the Long Key and the 7 Mile bridges in Florida, USA. 80s, 90s, the following decades saw the international expansion of the use of external tendons on bridges. In the picture, we can see now external tendons in the Tomoegawa Bridge in Japan. 1999, with the turning of the 20th century, it can be said that the external tendons had reached maturity, and we started to see international codes, regulations, and standards being published. 1999, as said, Germany made the use of external tendons mandatory for road bridges built with concrete girders. 2002, first international guideline for technical approval was published, ETAG 013, covering all type of post-tensioning kits, including sections specifically describing verification methods of external tendons. 2012, 10 years after the ETAG 013 was first published, FIB Model Code 2010 extended the content of the previous model code and included rules for design and detailing when using external tendon. And that leads us to today. More than 125 years after P.H. Jackson first patent, external tendons have become a fully developed technology with applications on post-tensioning of segmental bridges, post-tensioning of box girder bridges, and strengthening measures. Let me shortly present you now the primary components of these external tendons. So, anchor heads, wedges, bearing plates, long caps, short caps. Well, The list of different components in an external tendon can be quite long, but a lot of these components are common to all types of post-tensioning tendons. Therefore, I will now focus only on a selected few, which are specific to external tendons. And I will start with the main tensile elements and different combinations. As external tendons, we can find bare strands inside the global polyethylene duct with a filler, which can be either grout, soft fillers such as wax, grease, gels, and we can have the same configuration with wires instead of strand. Adding an additional layer of protection, there's the option of monostrands inside the global PE duct, all filled with cement grout. Still with strands, we can find some option, as just described, but without the cement grout. These have less layer of protection, and the outer ducts serve the purpose to help during the installation. The option is found both with round pipe and rectangular pipes. Finalized with this review of strand application, we will see also examples of single strands, either monostrands or epoxy coated. And we also find tendons on with post-tensioning bars. These bars are commonly found inside PE pipe with filler, again, either grout or soft fillers, or wrapped with a tape system. You see there's a quite big variety as opposed to internal tendons. We do not have typically all these combinations. If we move now to the anchorages, well, again, at first sight, anchorages for internal and external tendons are not fundamentally different. They can both be composed of anchor heads, bearing plates, anchor bodies, reinforcement steel, but there is one different that I want to bring your attention to. Anchor bodies or bearing plates can be cast in structural concrete in combination with confinement reinforcement only for new bridges or strengthening measures which include the addition of new concrete elements. Some strengthening measures, though, require direct load transfer to old concrete. In these cases, additional confinement and bursting reinforcement cannot be installed. And then usually larger, specifically designed bearing plates are required. In internal post-tensioning, the force is introduced continuously all along the length of the tendon. For external tendons, the uplift force is introduced through the deviators. Depending on the tendon layout and project requirements, a number of different solutions can be applied to deviate the tendon. We can have deviation around a sharp edge, which means radius close to 0. This is acceptable for deviations smaller than 2 degrees at both sides of the deviator. But for larger deviations, a positive constant radius is mandatory. These radii can be achieved with different solutions, whether it's making use of diabolos, using oversized pipes with the addition of inserts, or with pre-bent tubes. For band tendons, box deviators are specially made with rectangular section, typically out of steel or polyethylene. And for monostrand bundles, matrix deviators are cast in the concrete with tubes to individually deviate the strands. All these types of deviators need to be tested to verify the integrity of the corrosion protection barrier after stressing. The European assessment document, which has a very long name, 1600004000301, which replaced the ETAC 013, for example, define testing procedures for deviations with constant radius, as we can see in the picture, and deviations around sharp edges, as we saw in the previous slide. The acceptance criteria for all these tests is focused on the minimum thickness of the PE sheathing after the test. And finally, fixations may be needed to prevent transverse vibration of the tendons. Vibrations reduce the free length of the tendon. And depending on the geometry of the bridge, the size of the tendon, and the local codes or recommendations, this vibrating free length should range between 35 to 70 meters, as 70 meters, for example, was the case of a very long tendon installed to strengthen the Inbrücke Neuhaus viaduct. And with this, I get to the end of this first part of the presentation. I will thank you for your attention, and I will pass it to Teddy Tiria, who will continue with the presentation. I hope I will speak later to you in the Q&A session. Thank you again. To you, Teddy.
My name is Teddy Tirio. I'm going to present to you on durability and design aspect of this external tendon. First of all, I would like to show you actually the durability issue that happened in the past. As you could see on this picture, that this is a vertical external tendon in post-tension column. Where you see here is actually strand corrosion and then void grout. Second case down here is external tendon. It's a failure of external tendon in a box girder. And you could see here that it's quite dangerous when this tendon failed, and it happened suddenly. And if you are at the wrong place at the wrong time, so somebody could get hurt. So this is quite dangerous actually when external tendon fails suddenly. Let's first talk about the corrosion basics. You know, corrosion is really a deterioration of material or metal in this case because of reaction with the environment. So environment is really play a key role actually in formation of corrosion. So corrosion required oxygen and water to form the corrosion mechanism. So without one of them, no corrosion can be formed. So in our design strategy, we have to make sure that we are going to create a barrier against this agent that causing corrosion. So elimination of one or two of the following corrosion promoters is our objective in corrosion protection. So humidity, for example, larger than 40% of relative humidity is harmful to our post-tension tendon. Oxygen, water, chloride ion, stray current, and other corrosive agents. FIB conducted two workshops in the past, as you can see here in 2001 and 2004. The first one in Belgium, then second one actually in Zurich, Switzerland. This is a good resource for us to learn actually the experience from all around the world, how the corrosion happened on what project, and then what is the solution. So we hope that with this workshop and this document that we will learn and to be able to avoid the future corrosion actually durability issue on our future post-tension bridges. The typical root cause of external tendon durability issue is damaged duct, cracking in the PE duct. So you lose the protection. So grout void, actually the high point, the anchorage as a result of the bleed water. And grout void as a result of poor construction practices. Tendon corrosion failure as a result of water and oxygen intrusion. Actually, this is lack of corrosion protection. And also the tendon corrosion could cause by unsuitable grout material. And this grout material could cause soft grout, for example, that happened on several projects here in Florida. So tendon corrosion is really a result of shortcoming of specification and detection method. And I think we have learned quite a bit. Now we have to make sure we are able to apply all of the knowledge that we learned to our new project, then making sure that the durability issue that we have seen there is not going to happen again. Some owners have revised the policy on external tendon corrosion protection. For example, France and Florida Department of Transportation in the US have implemented basically using wax filler instead of cement grout. So both of these owners actually prohibited cement grout filler in the external tendon bridges. In Japan, using different approach, Japan adopted epoxy coated strand. But keep in mind also, grouted external tendon are still widely used in many countries. If this is done properly, and grout also can provide a good protection to your tendon. After the workshop, FIB have created a model. What type of corrosion protection? They depend on the structural protection layers and aggressivity and exposure to environment. So there's protection and action. For example, if you have very low structural protection and you have in a very high aggressive environment, so you really need PL3 protection level. If you have very high structural protection layers and very low exposure, what you need is only PL1. So what kind of protection? So each of the owner and consultant that design this bridge have to make sure that they follow the national code, whatever the protection of the national code required. But this is kind of guidance for the owners around the world. And the next slide here gives you the what is to show you PL1, PL2, and PL3 here. PL1 is really regular tendon where you still can use metal duct and grout it. And then PL2, this is have to be encapsulating. The tendon have to be encapsulated from end to end and leg tight and plastic duct, all of those. And then PL3, you need to add. PL2, add with monitorable and inspectable at any time. For example, using the EIT, which is electrically isolated tendon. Protection measure for pre-stressing tendon is typically is HDPE duct, cementitious grout, flexible fillers such as wax, grease, gel, epoxy-coated strand, and dehumidification, electrically isolated tendon. So we could use either typically combine some of these protection measures in our project. Now I'm going to move to the design aspect of external tendon. Why we consider external tendon in design of new structure. If you could see down here, of course, one of the benefit is that with external tendon, the concreting of the member can be improved because there's no internal tendon in the member. So you can have thinner member, ease of installation, and the most important also the replaceability. So you can replace this external tendon at any time. inspectability, so you can inspect them because they are external, so you can see them with your naked eyes. So ease of adding new tendon in the future. If you have any issue of deflection, for example, of the project of the structure, that you can add future tendon. So make sure in our design, we need to prepare an extra hole in the deviator and also in the diaphragm that for this future tendon. Essential design aspect of external tendon. And we also need to be aware that the behavior of external tendon is quite different actually with bonded internal tendon. And especially beyond the cracking level of the structure. We all know that there's no strain compatibility actually in external tendon with the surrounding concrete. And this is quite different behavior actually with bonded internal tendon. Fatigue is less a problem actually for external tendon. Typically, the tendon path is follow the polygonal shape formed by deviators. Deviators play a very important role actually in external tendon. So we're going to talk a little bit more later. So in design, of course, we use the equivalent PT forces introduced at the deviator location actually applied to our structure. So external tendon is assumed as unbonded in design, regardless of this tendon is grouted or non-grouted. So typically external tendon have less eccentricity compared to internal tendon. This is show you the deviator, because we have to properly design the deviator in order to make the external tendon work actually. A failure in the deviator actually that is mean a failure in this external tendon. So we have to make sure that the forces exerted actually from this external tendon is properly counted in the design of the deviator. And this picture show you actually the applied PT equivalent load from the external tendon applied at the deviators actually, and then finally is going to be subjected to the structure that we are designing. This is example give you actually external tendon with 2 deviators. And I think if you could see here, Guillermo, I think talk about the Diablo. This show you actually the different detail with the old conventional external tendon, where typically they are bonded at the deviator. Now in this case, actually we have Diablo, and the tendon is sliding actually in this deviator. So we can remove this tendon very easily. But make sure we have to design this Diablo properly, if you could see that. And this is the detail 3 and detail 4. And we also use actually Diablo. This picture shows you actually the load VS deflection. If you can see from this diagram that from zero load to the cracking load, actually the behavior of bonded tendon and unbonded tendon, they are exactly the same. It's no different. When beyond the cracking load, so the behavior is quite different. If you could see that bonded tendon can achieve higher ultimate strength than the unbonded tendon. The design method at feasibility limit state load combination, actually there's no difference actually between bonded and unbonded when you do the design. At ultimate limit state, the unbonded tendon stresses are typically lower than the bonded tendon. So how the ultimate limit state stress computed or estimated? In general, there are nonlinear analysis these days that can be done. There are a lot of software that can handle nonlinear analysis for external tendon, and also empirical equation quite often also used to estimate actually the ultimate stress of unwanted tendon. And in the US, for example, ASTO LRFD code actually have used actually empirical formula to estimate actually the ultimate stress. On the other hand, Canada used different approach, and this is the most conservative. And in Canada, when you design external tendon, that the ultimate stress is at the same level of your effective stress in the tendon after all losses. This is the formula in the ASTO LRFD that commonly used in the US. This is the Canadian. That Canadian actually just use whatever you have at the effective level. So that is where your ultimate is. We did some study actually at the FDOT on the differences between nonlinear analysis and this with this formula. And we found out, of course, nonlinear analysis is a viable and the most accurate tool in predicting the ultimate stresses of unwanted tendon. However, it's time consuming, required accurate material properties. So empirical equations are practical and provide a very reasonable accuracy in prediction of unwanted tendon ultimate stresses. Now, it's also important, like to mention the the future tendon, that when we design external tendon bridges or even post-tension bridges, that we need to provide the future tendon provision in the form of extra hole in the deviator and also in the diaphragm. So both ASTO LRFD and FIB 2010 required a minimum 10% of the primary pre-stressing forces actually for your future tendon. So you can insert a future tendon actually to add to your structure. So with this, I would like to show you two examples of project that utilizing external tendon. It's quite different strategy. If you could see, this project is Bergen Viaduct in Germany. Actually, this project actually use external tendon with prefabricated 66.7mm wire with wax filler. And then one of this project, this is in Florida, actually USA, called Sunshine Skyway Bridge. This is 30 years ago, of course. This bridge actually utilizing external tendon, almost with the whole bridge actually from the main span of the cable stay, including the high level approach. They are all precast segmental, and the external tendon extensively used for this project, including thousands of external tendon. What you could see here is using 19.6-inch strand with cement grouted. Of course, with a new project in Florida, we no longer allow cement grouted actually in Florida. So we're using wax now. With this, I'm going to close my presentation. Thank you for your attention. I'm going to transfer it to my colleague, Christian.
So, hello everybody. My name is Christian Gläser, and in the following minutes, I want to talk about external tendons in new structures. So after we learned about the key components, about design and durability aspects in the previous presentations, in the following, I want to focus really on the installation of the various PT or external tendons we are using, and will guide you through the key elements before, during, and after the installation of these tendons. So, as most of you know, there are different types of structures, and I tried to classify in two types to say there are external tendons that are used as primary post-tensioning, so that are really tendons that are installed, stressed after casting of the individual span with simultaneous activation of the self-weight. So that means these type of tendons are in the critical path of the bridge construction. And additionally, we have external tendons used for secondary post-tensioning. That means we have usually the entire bridge completed, all spans completed, and at the end, for the live loads, external tendons are installed, which is at least for Europe and Asia the majority of all applications. So in the following, I will always differentiate between three major types of tendons, and the difference is coming from the different way of assembly. So there will always be tendons that are on-site assembled, there are semi-prefabricated ones, and fully prefabricated tendons. And there are, of course, a lot of pros and cons for the individual ones. And I will guide you quickly through the key differentiators, but in the following, I will consider this in all the installation aspects. So starting with on-site assembly, for sure, it's the most flexible and most frequently used method. Installation quite similar, or stressing and so on, quite similar as you know from standard post-tensioning. So that means we are using similar equipment, of course, maybe special equipment for the corrosion protection. We'll come to this later on. The components are separately delivered to the construction site. What here the negative aspects are is, of course, if this is in the critical parts of the bridge construction, of course, all the time constraints are here quite important to consider. And the corrosion protection perspective, of course, it is applied on the job site. That means we have influence from the weather, from field conditions, and so on. Coming to the partial or semi-prefabricated method, so the advantages here that the free length of the tendon is prefabricated. That means here, for example, corrosion protection on the free length is applied under constant conditions, considering weather, considering even that you have standard working procedures in a plant instead of the field. Still, you have the chance here to adapt the length of the tendon on the field, but on the connection to the anchorage needs to be done on the site. And that's one of the negative aspects, that the prefabrication and thereof also the corrosion protection is only done in the plant for the free length. So that means especially this connection to the anchorage and the anchorage zone itself needs to be corrosion protected on the site. And already, well, there are some limitations for size and length of the tendons as this is prefabricated. Coming to full prefabrication, well, this means a prefabrication including the anchorages, and in case of the external tendons, that's easy to do with having both anchorages installed, connected with the duct, and to even have this connection working during the stressing. This needs to be a tension stiff connection between the anchorage and the PE tube. So advantage is, of course, corrosion protection can be applied under factory conditions, so standard processes, no weather influence, good quality control. The complete product is then shipped to the construction site more or less just in time or directly prior to the installation. What's the negative aspect here is, of course, there is almost no adjustability of the length on the side. So that means before the tendon is produced, an exact determination of the tendon length is quite important. So with these three different types, I will now walk through the different steps, starting with job site activities we have to do before the bridge or the bridge segment is casted. So here a lot already really high requirements are for the geodetic works. So that means we need to ensure the free passage and the correct profile of the duct or of the tendon through the entire parts of the tendon. So starting with really a very accurate positioning of the components, fixing them, and also having really here a detailed look into, let's say, all deviation areas. So after the concrete is hardened, or once we are ready to install our external tendons, we have to take special care for a correct positioning of the deviators. So you see, for example, a solution with these half shell elements that needs to be exactly placed in the deviation pipes to have to enable here really a good, a perfect deviation of the tendon. All deviation zones need to be clean and prepared to allow a proper elongation to avoid any damaging of the duct during the installation. Temporary intermediate supports along the straight lengths are required, and of course for crowding vents at high positions are required. Temporary corrosion protection is essential, so you know that the pre-stressing steel needs to be protected at any time. In case of a prefabricated fully encapsulated tendon, that's quite easy because the corrosion protection is already applied in the factory, so that means no special care needs to be done during the installation or before and after stressing, because the tendon is already corrosion protected. For the other cases, we need to make sure that there is only the that we are taking care that the time between installation, stressing, and corrosion protection is limited, and the permissible time slots that are specified, for example, in Bulletin 20, FIB Bulletin 20, are roughly 4 weeks, and in case we have aggressive environment, this should not exceed 2 weeks. So if these times cannot be met, temporary corrosion protection is required. Coming to the installation itself and starting with on-site assembled tendons, first step is the assembly of the duct system on the entire length of the tendon path. So the duct usually is shipped in parts. So that means the individual pieces of the pipes need to be connected. So typically this is done by electrical welding. And when, of course, there are also some cases, and we have seen in the slides from Guillermo, for example, if pre-installed bent duct pieces are part of the duct, they need to be included as well. Coming to the strand installation, so this can be done either by pulling or pushing the strands through the duct and fixing them at the end anchorage. And again, of course, latest here we have to double check that really everything is absolutely clean and absolutely prepared to allow a proper elongation. Coming now to the partially prefabricated tendons, so usually they are pulled into the duct. So here, of course, it needs to be considered that the duct is not damaged during this pulling process. And in the anchorage zone or close to the anchorage zone, the sheathing is removed before connecting the tendon, the partially prefabricated tendon, to the anchorage. In case of the fully prefabricated tendon, installation quite similar. So that means, again, pulling, considering that we are not damaging the duct. But here the advantage is that the anchorages are already assembled. So this means now we can directly stress it. We don't need to remove anything, any sheathing in the anchorage zone. So it can be directly stressed and when fixed by split shims and thread nuts at or thread nuts at the end anchorage. Stressing itself, starting with some general aspects. So standard process is quite similar as we know for internal pre-stressing. So we also make measurements during the stressing at several load steps and at the final load, so like force and elongation. But what is additional and what is quite recommended to do is also measuring the movement and the elongation of the duct or sheathing over the full length, especially at the deviation zones, to really see if if there is any, let's say, untypical movement, and that should be, of course, then identified if this is happening. Now, focusing on fully prefabricated tendons first, because it's the easiest one to describe. So here, the tendon is stressed after it's installed. So the final length is just achieved after the stressing. So that means in the beginning, the tendon cannot directly be picked by a check. So that means the stressing is done by a stressing spindle, as you can see in the photos on the right. While stressing, the extension of the fully prefabricated tendon will move towards the bearing plate, and at the end, when it is fixed by ring nuts or the shim blades, as shown before. For the other types, on-site assembled or partially prefabricated tendon, it's the standard stressing procedure as usually done for internal post-tensioning. So that means the anchor head remains fixed and only the tensile elements elongate during the stressing, and when usually by strands, when these tendons are anchored. Quite important message is, of course, here cutting off of the protruding pre-stressing steel shall just happen after the designer has accepted the stressing record, because after this it will be difficult to unstress the tendon again. Some special application or special type of tendon is quite frequently used in the Benelux area. So here I'm talking about bundles of monostrands inside a PE duct that's filled with the grout. Here, the stressing procedure is a little bit different. So an initial force is applied first to remove the slack on the tendon. After that, then the ducts are grouted, and after the grout is hardened, the tendons are finally stressed to their final force. So that's the stressing. Just some comment on possibly restressing. Restressing is possible as far as we can guarantee that, for example, wedges will not have the same gripping in the areas that originally was done. So it's recommended always to have an additional elongation of minimum 15 millimeters to avoid any fatigue problems in the free length. Duct filling or corrosion protection is then the next step. So that means for all types of tendons, this needs to be done either in the factory in case of the prefabricated ones, or for on-site for the tendons that are assembled on-site. So, and in principle, we have always the same requirements. So we need to guarantee that the complete filling, that the tendon is completely filled, and we are avoiding any voids in the filling. And of course, we have to consider that all the requirements on the material itself are met. Starting with partially or fully prefabricated tendons. So for these type of tendons, only soft fillers can be used, because otherwise a coiling will not be possible. So the fillers are typically fillers that needs to be warmed up or have a thixotropic behavior. All the ducts have inlets and outlets or vents to allow allow a proper filling of the duct. And during the duct filling, of course, a quality control needs to take place. In case of monostrand tendons, usually all the protection on the free lengths is directly done at the strand manufacturer. So usually the strand manufacturer is directly assembling the extrusion of a PE sheathing over the grease layer on top of the strands. For on-site assembly, I'm focusing here on soft fillers, but it's in the Bulletin we are also describing it for cementitious grout. Just some thoughts here about the way of the injection. So of course we need to, especially in case of soft fillers, we need to make preparations to avoid that leaking soft fillers can reach the groundwater. So that might be an important thing to consider quite early in the job site planning. So typically all anchorage zones, all deviation areas needs to have inlets and outlets to allow really a proper injection. So you see in the sketch on the right-hand side, that at least you need one inlet, and at all high points, anchorages, and so on, also outlets are required. Additionally, you can consider for high points also special outlets, as you're seeing in the second picture, or you can do the entire injection with vacuum injection. That is, of course, the most, let's say, sophisticated method, but all these options are available. So we need to make sure that really all the soft fillers still are liquid, so that really everything can be filled, especially the high points. And as I already mentioned, it can be necessary to re-inject these areas additionally. Well, just some photos on a typical layout for on-site assembly. Quite important, as I mentioned, is the quality control. So there are different ways, for example, by temperature measurements, by knocking with a hammer, and a lot of different aspects, as you can even see here. After the stressing, the corrosion protection on the free lengths is done, some final works need to be done. For example, the corrosion protection in the anchorage zones, closing possible openings on the free lengths. We need to install the fixations, as you see in the left photo, as we have seen, or as was described by Guillermo before. Documentation, well, we need almost the same as we have for the internal post-tensioning. So we need calibration certificates for the stressing equipment. We need to prepare and submit the stressing records with force elongation and even the comparison between calculated and actual elongation. Well, finally, just some words about quality control during the execution. So at all stages, also quality control by an external party can be necessary and recommended. So before the stressing, all the calibration documents should be checked that they are still valid and so on. After the stressing, we should really do a first visual inspection of all the tendons, for example, checking the corrosion protection that really it's fully filled by knocking on the tendons to see really that they are fully injected. Yeah, now I've talked such a lot on soft fillers, but we will and shall not forget the grouted tendons. And all the standards that are in place around the world applies, for example, specifying the material and also the verification methods. So for Europe, for example, Euro norms 446 and 447, and also a lot of standards, as you can see here, for North America, and also additional specifications for the individual DOTs, Caltrans, and so on in the US. Yeah, hopefully I could give you an overview about some major aspects during installation of external tendons in new structures. And I want to hand over to Hermann Weyer, who will now focus on repair and strengthening, and that's related to existing structures. So Hermann, can I take over to you?
Thank you, Christian. I'm talking about using external tendons mainly in strengthening projects for bridges, but also some other aspects. I will not show a lot of text this time. The text you can read in the FIB Bulletin, and everything is described in there quite well, and will focus mainly on some pictures. I will cover 3 topics. One is replacement and repair of tendons, just briefly. The second one is measurements and monitoring of external tendons. And finally, I focus on case studies for strengthening of bridges. Replacement and repair of tendons sounds a little bit as if there is need to do that. Usually they are very shiny and have very good quality. And one big benefit in construction is that you can have access to the tendons and you know what happens there. And in some cases, damages are not avoidable. Here you see a kind of improper saddle type. It's improper because it cannot compensate for misalignment. And in this case, you have a damage at the corrosion protection. Usually damages for the corrosion protection can be repaired. Here, one repair method is just to make a hull around the whole deviator and to fill it with, e.g. with wax, making sure that no air is entrapped. And by that, you can upgrade the tendon again. If you have structural issues, then of course replacement is the preferred method. And here we have a second benefit of external tendon, that it's not only accessible but also replaceable. For replacing external tendons, some procedures can be followed. If you have a grouted tendon, first you need to remove the existing one, and then you can install the new one. For the installation of the new one, you can follow the explanations Christian had given. For deinstallation of the old ones, you can follow step-by-step procedures as described in the Bulletin. For grouted tendons, this can be quite dangerous if you cut wire and strand by strand. The force can be reintroduced by bond into the other strands, and finally you can have a brittle failure of the tendon. It can hurt, and special care is needed for that. For soft filler, this is quite easy. You can detension, or you can cut strand by strand, and each one is detensioned individually, and usually you have no big problems there. The second bullet point, measurements and monitoring, mainly all is about the load measurement. Everybody likes to know what is the load in the external tendon. What you can do is you can do lift off with a check, as you can see here. Either the check is gripping the strand or the bar directly, or the check is gripping the wedge block. In any case, if you do that later on, you need to remove the cap, and you need to make sure that after that, if you close it again, that the corrosion protection is upgraded. There is a preferred method, which is vibration measurement. That means you are measuring the acceleration, and together with the span of the tendon and the mass of the tendon, you can derive quite well the tendon force. There are more methods like load cell and magnetoelastic sensors. These sensors need to be installed mainly prior to installation, but there are also solutions like here at the bottom that can be installed later on. And with these measurements, you can also achieve long-term measurements and permanent measurements. Of course, there are more measurements that can be done. One is the elongation of the duct to know about the sliding mode and so on. So this is important at deviators. For some tendon types, you can measure temperature, of course, volume of grout or wax that you bring in, and also the pressure of the grouting. Finally, I come to case studies of strengthening of bridges. External tendons are very, very good and very cost effective if it comes to an upgrade of concrete bridges. Concrete has a very good compression resistance, but with the help of the tendons, you can activate that also for bending and tension. This is either you you make a renovation of a bridge or you upgrade a bridge for higher load models. And external tendons are also effective because they are acting against the dead load also, and not only against additional loads like passive strengthening measures. And if needed, you can have an uplift force. At the bottom, you see one example, longitudinal section of a concrete bridge, T-beam, which is strengthened with external tendons. In green, you see the tendon path, and you have a very little contact to the existing structure. It's mainly at the anchorages and at the deviators. I'd go on to longitudinal tendons. You can apply them just straight, like this strengthening measure close by Munich. Of course, you can be active against the bending moment better if you deflect them, like here. There is a deflected tendon on the left inside a box girder, and on the right it's outside a T-beam. So here you can see quite good the connections to the old structure. You need to be very careful here, but I will discuss that later on. Of course, you can mainly strands or wires are used for longitudinal tendons, but also bar tendons can be used. In this case, only straight pre-stressing is possible. In addition to longitudinal tendons, we have transverse tendons in new construction. In the past, this type of tendon had been used internally, but the state of the art at the moment is that you are covering all transverse forces with internal rebar. Maybe just the deck slab is pre-stressed. But for strengthening, you have no choice. You need to apply. And if you actively like to act against the dead load, which is important for concrete bridges, very heavy concrete bridges, then external tendons are very important. So here you see vertical tendons, but against shear and torsion. But also horizontal tendons are possible. Here, this is against horizontal shear at the connection between the webs and the bottom slab. Coming to some details, anchorages can be either supported at old diaphragms or they can be clamped to the web. If you have a support against an existing diaphragm, you have no choice or opportunity to arrange a spiral or so, then you need quite massive anchor construction to get the high forces into the structure. Of course, you need to design whether the diaphragm is able to resist that. You can strengthen the diaphragm at the backside. There are different possibilities. On the top, you see some high-strength concrete anchor plates, quite big. These are following this principle. And at the bottom, you see massive steel plates, or on the right, you see a steel plate construction. It's very common that forces up to 4, 5, or even 6 meganewton per cable are introduced to an existing structure. So that's why you need massive anchorages. But the big benefit is you need only few of them, since cables can have a length of several hundred meters. Of course, you can also apply anchor beams if you like to transfer the loads to several points. Here you see vertical anchor beams at the diaphragm, pier diaphragm of a bridge. And it looks like it's a tendon. Here is the anchorage. This is the over length of the cable. And you see the massive steel plates also here. But very often you don't have the space, or the end diaphragm is not accessible. Then what you need to do is you need to clamp the anchorage to the web. You need to consider any torsion you introduce to the structure or any bending to the web. So this needs to be compensated by stiffeners. This is usually done by the designer. But the anchor zone, as Guillermo said, looks very similar to internal bonded tendons. And this can, at the end, it looks like that. You have here an anchor block made of reinforced concrete with the external tendon anchored here. And it's connected actively by transverse tendons to the existing web. Here you see again this anchor block. This is all done with in situ concrete. Of course, it's also possible to do that with prefabricated elements, like you see here from an example from Hammersmith flyover with prefabricated ultra high performance concrete. For bars, this all is a little bit easier because the forces usually are smaller. Another strengthening example for the horizontal shear between the box web and the bottom slab. And you can have here a little bit larger plates, but you need to be careful. You don't have a spiral in that web, so that so you need to choose sufficiently big plates. Of course, also anchor beams are possible for shear strengthening. Vertical bars, you have here fully one with steel, but also a new type with concrete is possible. And on the right, you see also vertical anchor beams. This is mainly to transfer the load from where you need it to where you can get it into the structure. After the anchorages, a second crucial point are deviators. They need to be formed inside the existing structure. And yeah, usually this is done by creating holes in diaphragm in the pier regions. So you drill a hole and then you either insert one of these half shells or you bring in a bent pipe and grout the voids in there. These are, but this is the first time I addressed this. Coring or drilling boreholes is very important for that kind of activity. The other solution is if you clamp the deviator to the web, usually you need to do that in the field region because very often you don't have a diaphragm there. Or if you have a diaphragm, usually this diaphragm is very slender and so that you cannot house the deviator there. So what you need to do, first of all, in the background, you see the old structure. There are existing tendons. You need to be careful not to destroy them. So you need to look. Then you fix some rebar there, and then you install the deviator, put some extra reinforcement. In this case, you have even 2 vertical post-tensioning bars to bring the force down to the bottom of the structure. And finally, you pour the concrete and build this new diaphragm. Deviator. Deviators clamped to the web can also be made of steel. As you see on the left, it can be a quite complex element. And it's a suitable method, but you need to be careful that corrosion protection is done properly. And of course, it's not really suitable if the deflection is very high and the pre-stressing force is very high. So for large units, it's quite difficult. So after the 2 details, I come to the very crucial issue for strengthening measures. The tendon path, as Christian said, is very important. The tendons need a free passage of the tendon and are not allowed to touch the old structure. So the tendons need guidance by deviators and spacing by creating holes. And before creating holes, you always need to look that you do not destroy things inside the structure. And it would be preferred if you check this before you start the construction. And these are typical bore drilling devices, and they are very powerful and very accurate. And we made the experience that up to 10 meters you can drill through reinforced concrete with a deflection of only 10 centimeters. So this is possible. On the right to the top, you see a special device, again done by or used that for Hammersmith flyover in UK, and there a lot of holes had been drilled simultaneously. This is definitely a special device. So on the left you see standard devices. So another example how important it is to check the situation on site. On the left you see the web of a T-beam bridge with existing tendons, and you really need to look where you bring in the borings and the transverse tendons to fix the deviator for the longitudinal tendon. So this is very tight, but if you are looking for the position of the existing tendons, then it's possible and can be done. So on the right, you see the face of a bridge, and it makes sense to mark all the existing tendons. In red, you see shear strengthening tendons inside, and the blue net or blue grid are the rebars inside. So these had been some points that are addressed in the bulletin. If you have questions, you can ask the questions to us now, or you ask the experts of the task group. You find them in the bulletin. One of them is walking through this structure, or you just look into the bulletin. And I close the presentation now, and we'll start the session with questions and answers.
Yeah, maybe Hermann, I directly take over. There had already been some questions to Teddy, and we replied in the Q&A session. But I left one, and there are two more to you. But to give you time to brief, maybe after presentation, I quickly start with the one from Joachim. There was the question: how is a long prefabricated tendon handled and placed in position on site? What kind of lifting equipment is required? So maybe a quick answer on this. So these type of tendons are usually shipped on drums to the job site. So for these drums, some special uncoiling devices are available. So these drums are then placed into these uncoiling devices. These uncoiling devices are either directly fixed on the deck, on the bridge deck, or are, if it's not such a very long one, even still hanging on a crane. So of course, special care needs to be taken when designing these uncoilers, because especially there are really strong brakes needed, because you can imagine once you start pulling on such a drum, if you don't have the brakes, it will never stop when you like it. So, but generally by considering this, tendon lengths, well, a little bit depending on the size of the tendon, but tendon lengths up to 400 meters shouldn't be or are typically no problem. And well, what I forgot to mention is that the tendon itself, well, the uncoiler is on the deck, and the tendon itself is pulled into the box girder, for example, by having holes in the bridge deck. And of course, we need to take care to consider that there are no sharp edges, so that really this tendon can be pulled in. So hopefully this is sufficient answer to the question. And maybe, Hermann, I hand over to one of the questions that are related to you.
Thank you, Christian. I answer now to the question of Mohammad Riduhan Natino. So you are asking how to evaluate the required quantity of external tendons for a certain bridge structure. Well, usually it's important to start with a static calculation, and you assume a certain pre-stressing force and uplift forces if you apply deviators. And once you found within your static calculation the forces that are really helping you with your design, then you check how can you introduce the forces to the structure. Of course, if you have a box girder and or a double T-beam, then on both sides of the structure, there should be the same number of tendons. So you have a kind of symmetry. This is one aspect. And also for kind of redundancy, I would always install minimum of 2 extra tendons. And finally, if you come up with a tendon size of 100 strands, then definitely this is not, well, it's not easy to install and realizable. So I would split it down to sizes that are common and can be installed on site. So a typical size is, I would say, between 3 and 4 meganewton. This size you can install quite easily, and you also can anchor it easily. And by this procedure, you get at the end either 2 or 4 tendons for a typical structure. Okay, then we have another question of Frédéric Monet. And may I ask Teddy to answer to it?
Yeah, one of the benefits of external tendon, especially in the inclined part of the tendon, is to help shear strength. So the vertical component of external tendon actually can be counted actually to contribute to the shear strength of the member. But I'm not quite understand here in the question about the passive part of the tendon. Is it, I assume, passive part, is it the straight section? Maybe of course, the straight section where you don't have the vertical component, so you cannot take those into account actually to contribute to the shear. I don't know, Herman, do you get, I think, what the question about the passive part of the tendon?
Well, the tendon strength or external tendons cannot be directly, I would say, cannot be directly used for shear resistance because they are not. Yeah, you cannot make a design at the cross section. You only have the force introduction at the anchorages and the deviators, and there, of course, you can apply the vertical and nominal, the vertical and horizontal parts of the force. But definitely for shear, it's very helpful because the concrete is pre-stressed, and if it's pre-stressed, you can usually apply a flatter angle of the compression strut in the webs, and by that the shear resistance can be increased. So less rebar is needed for that. And that's why this pre-stressing the global pre-stressing with external tendons is so helpful. Of course, it's needed that the compressive strength of the concrete is sufficiently high. For strengthening measures, this is usually given because you have quite a lot of hardening in the long run during their lifetime. And also for new tendons, you can increase the concrete strength. I hope this was a good answer. There is another question by Adi Obaida. What drilling for the tendon path, is very important, and definitely you need to look into the structure. You cannot, I never would try to cut a post-tensioning tendon in the diaphragm. In the diaphragm, it's you can have bars in there, but it's not affecting the quality of the concrete, in my opinion. It's only removing some section of the concrete if the core is quite big. This, of course, need to be respected, and cracking never has been seen. In my opinion, usually this is not a big issue. The designer of the strengthening method should take into account that a void is created in the structure, and that maybe some rebars are cut through.
Okay, maybe we have time for another question. There was a question on testing procedure for external tendons. We said that TAC 013 was defining specific methods. So the question is, how is in terms of static resistance, how does it compare internal and external tendons in these guidelines? So the procedure starts the same. We will stress with the standard equipment with the same jack as we will be using on site. We will increase the load until 80%. And then this load is transferred to the testing rig. That's a normal procedure. From there, we will go to breaking load, but it's not the case for external tendons. For external tendons, this force will be held constant for 2 hours. Then we will unload to 20% of the load, and then we will go to failure. So that's the test will take longer. And during this 2 hours, there is some measures taken on the anchor head. We're monitoring basically the deformation in the same plane and compression. So we take these additional measurements because are relevant, since the external tendon being unbonded to the structure, it will be seeing the load for the entire life of the tendon. Okay. I hope this addresses that question. And I don't know, Christian, do we have time for more questions, or?
I can answer this additional question of Frédéric Monet. He's addressing that if you pre-stress up to 0.7 of nominal breaking load, you will have a part of the tendon which is not activated. Yeah, this is true. The activation for bonded tendons, for internal bonded tendons, you can do in the design. Of course, you can go up to the yield strength. But for unbonded or external tendons, it's yeah, quite difficult to activate a higher force. Maybe you can, but then I refer to the presentation of Teddy Therio. You need to make sure that, or you need to prove how the increase of elongation is in your unbonded tendon. Usually the increase will be very little, especially if you have an external tendon that is running for 4 or 5 spans. Then yeah, a load in ultimate limit state in one span would not really increase the stress and elongation in the external tendon. So in any way, either you do not activate that, or you need to prove in your design that how much you can activate.
Okay, so I believe with this we should close the discussion here, at least during the live stream or during the webinar. I've seen there was just another question coming in through the YouTube channel, but I believe we'll give the answers later on. So on behalf of all the presenters here, I want to thank you quite a lot for the participation in this webinar, and I hope it was interesting for all of you. And I want to thank again all the colleagues in the FIB Task Group 5.8 who participated here in preparing the Bulletin, and we tried to give you, let's say, or present to you some of the content of the Bulletin. Hopefully you are now all also quite excited to learn more about external tendons, and the FIB Bulletin 97 is published and is available via the FIB website. So thanks again for the participation. Hopefully it was interesting for you, and take care. Thanks.